Hello and welcome to our webinar. There's no plan like backup plan. Get ready for disaster recovery. We know IT has a lot of redundancy within disks, servers, power network, and many more. There are backups, they are hopefully offsite. But what do you do if a data center really goes dark or light up? This is what we want to discuss today. Thank you for being here. My name is Michael Kantner. I'm a senior pre-sales engineer at OVHcloud, one of your hosts today. I'm joined by our great partner, Instinctools. Mehdi, would you like to introduce yourself?
Hi everyone, thank you for joining us in the webinar today. My name is Mehdi and I'm Managing Director at Instinctools. Very happy to have you all here. I'll give back the word to my colleague Michael. He will start the first part, and after the first part, I will take the application part.
All right. Thank you very much. So why are we here? We're here because disaster recovery is really underrated in IT, but it's a crucial part of business continuity, especially for digital businesses. As an IT service provider like us, we offer a lot of possibilities, but by far not all of our customers uses them. There are many excuses, but fewer arguments to do so. It doesn't matter if you have classical IT infrastructure, your data center on-premise or hosting or wherever. If you're using bare metal virtual machines or monolith applications, there will be a way for disaster recovery every single time. One may be better than the other, but there is a way. Those of you who are already utilizing cloud technologies, especially Elastic or containers, may have better options, but for most, it's a challenge nevertheless. Before we start, we need to clarify a few wordings. So what is a disaster in the first place? A disaster can be defined as a complete site goes down. So if you have a data center location made on your premise or a hosted data center, if this complete data center goes down for any reason, this is disaster for every IT infrastructure. It can be determined as the disaster hits when critical components goes down. But what are critical components? So disaster recovery is crucial, and it's really a component of business continuity to go on if something hard struck. When we discuss about disaster recovery, we need to clarify a few words. For example, RTO and RPO. The terms may be known for being used within backups, but it's also a special thing for disaster recovery. So if you have a backup, you do step-by-step backup. The last backup you took is the recovery point objective. So the point where your last backup has been in place. If you had an accident, an incident, or disaster, you may lose every data since the last point of recovery. But what time does it need to get back online? This is the RTO, the recovery time objective. It's crucial to determine if you need really fast going back online for your critical systems, or maybe it can take hours, days, maybe. But you need to define this to be really ready for a disaster. The most common way of being ready for disaster is if you do your backup and you host it offsite. So you're taking your backups off to another data center, to a safe, maybe back to home for some reason, but you have your backups ready if the complete site goes down. But have you really thought about what you do if your primary site goes completely black? You need to have the resources in place to go on. You need to know which application you need to start first. So it's crucial to know how your applications reference to each other, how they are interconnected. What do you do with your namespaces? What do you do with your IP addresses? So everything has to be in a plan, in a big plan. This is the reason why most companies don't do that much of a disaster recovery. They don't have the time or the will or the resources to do so. In many cases, even the documentary of your IT infrastructure may not be that good to be back online. The challenge is to have a strategy to do what you need to do if a site goes dark. One possibility to do so is having like Certo in place. This is something, for example, OVHcloud offers. This does an online replication from one site to another site. This can be stored offline if you want to, but it can be stored online as well. So it's a matter of how your infrastructure has been designed. What company may do is having a replication site, for example, an active passive setup, where you replicate your data to a second data center or a second application or a second database or whatever. This can be used, for example, for things that can't be load balanced. Classical monolithic infrastructure, for example, is one of the cases where you can't do an active replication, but you need to have an active passive, where you have your infrastructure ready, so that in the case of disaster, you can fire up those machines. This can be really expensive if you need to have your resources ready whenever you need it. But with a partner like OVHcloud or another data center hoster, where you can receive even bare metal instances within minutes, everything you have to do is have a plan ready to fire up your machines. When you have the possibility to replicate and have your instances ready online, then we have something we call active hot standby. You can replicate your data, you can replicate your machines to another site that is online, but it's not using. So it has not been used by access the data, but only for a background replication. The way of doing this is like asynchronous replication or something like Certo. And with the flexibility you may have in the cloud infrastructure, your instances don't have to be fully sized. They can be smaller in size. So you can have your minimal viable configuration ready and hot standby and replicated from your data. And in case of disaster, you can scale those machines up. This can be done automatically or manually as you wish, but you need to have the infrastructure and the plans ready. This is most commonly used in scale out and scale up scenarios. For example, if you have data center replicated to the other side. In case of failover, you're able to scale things up and be ready online within minutes. But the prerequisites for that may differ from everything else, because then you have not an infrastructure anymore where a single server can do a single thing, but you need to have replicated instances for this service. And if you do so, the step is really close to have an active scenario, which is, in my opinion, the best way of doing data recovery, because you don't need to recover any data because you're online within a second data center. This is the best way to prevent disasters. So if one side goes down, the other is still up. But this needs to have a geo-redundant load balancing. You have to have applications that are able to be run simultaneously on different sites. So an asynchronous replication may not be enough. Maybe you have to do synchronization replication, but this depends heavily on your infrastructure. But the top side of this is that you can utilize all the resources you have in place. You don't have like that budget within a second data center, because you can use all your data all the time. When you're using an active replication, it's heavily dependent that your application is ready to be synchronized. And this can be a really big challenge, especially with older infrastructure or older software. But there are several ways to do so. From an infrastructure provider perspective, It is easy to tell you that you can replicate your virtual machines, but it's not that easy to replicate your data within your applications. This is the reason why we are joining up with Instinctools, who is really well known for deploying your infrastructure in a manner, in a way that you can do like active-active setups. For the definition, what you can achieve is reason to determine what is critical to you. You have to keep in mind what is the data needed, what do you need to go on to move on with your business, for your customers, for your employees, and for your business as well. So there are several ways to do so. Do determine what is really needed for your business, do a plan, and especially do test your plan on a regular basis. The best practice is to have 3 different copies of your data in a live system, in a backup system, and in an offline system on 2 different media. This can be a disk backup, tape backup, or in most common ways, the cloud on object storage backup, which at least one of them is offsite. With an object store backup, it's easy to be offsite, and most common backup software do provide this possibility to have an object storage natively with S3. Veeam, for example, can connect to S3 and any object store and place your data encrypted offsite in another data center. You have to do your checkups if there's no error, and then you should be the safe side. From an infrastructure perspective, we have different products to cover you in your infrastructure. For offsite backups, we have Veeam, we have OVHcloud Connect with deduplication online, object storage and bare metal object storage servers that can be used for backup servers. For the code standby setup, we provide bare metal servers, hosted private cloud, public cloud, and of course, something with Terraform, where you can define your infrastructure by code and deploy it on a cloud on command. I think Mehdi will stress Terraform a little more. For active passive hot standby, there's already the place with bare metal servers that can be provided within minutes. The hosted private cloud, public cloud as well, and Certo for online replication of your on-premise VMware infrastructure or from another data center infrastructure to OVHcloud's data centers. And of course, for active, the most advanced way to prevent disaster, there is managed Kubernetes as well. And of course, the VRAC technology OVHcloud, which connects your data centers in the background through all our products and all our data centers. Talking about active, the replication methods for your services may be prepared for that, or maybe not. But what do you do if you are prepared or not prepared? Something Mehdi can tell you a little bit more about. So, Mehdi, would you like to go on?
I would love to go on. Thank you so much, Michael. Michael talked about how you can modernize your infrastructure to be ready for disaster. One aspect is also very important is how to modernize also your application layer. To go deeper into that part, I need to start with introducing a little bit or explaining a little bit what monolithic applications are. So a monolithic application has a single code base with several multiple application packages and modules. Each module has separate business logic. This is a type of application has, let's say, a single build for the entire application and is delivered as deployable, basically. A huge monolithic code causes complication for developers in understanding the code, and scaling of the application becomes challenging as with more copies of the monolithic application, there is let's say an exponential increment in memory consumption, bandwidth consumption, I/O traffic, and disk volume consumption. So different components had different resources, also resource requirement. So basically, one component may have more CPU incentives, other component need more memory, and due to the monolithic nature, you can't actually scale each component individually. So loading large monolithic application code into, let's say, an IDA leads to frustration. There's a large, let's say, a code base often require undesirable long compiling time. Also, it adds up to frustration making a single line of code change, basically while you're moving from A to B and you need to adjust a couple of things. It means basically compiling everything from scratch. It becomes more difficult to change the underlying technology, the language, and the framework because everything is tightly, really tightly coupled and depends on each other. Dependency management is also a problem in monolithic infrastructure, as any changes in one module require the entire application to be recompiled and redeployed. All components of the application talk to one database, really only one database. After some time, the database becomes huge, and we need to scale the database. And this is one of the problems in disaster recovery, like migrating a big database is much harder than migrating or, let's say, redeploying smaller ones. And of course, if the database fails, the whole system fails. So I have this single point of failure, which is not very fun. On one application model might require a different database system with different capacities from other models, but in monolithic architecture, you're limited to one single database. So if a specific feature is not working in a single module, it could take the entire system down. So to handle the issue, the system has to be patched and rebuilt, retested, and redeployed, which in a big application takes a lot of time, money, and effort. So the alternative for the monolithic architecture, or let's say the old school way of building architecture, is microservices. And I will talk about the characteristic of microservices in the next slide. So a microservice architecture consists of let's say, a collection of small services. Each service itself is contained. It implements a single business function. It should do one thing only and do it well. So these are small, independent, and loosely coupled. Each microservice is separated, has a separated code base, and can be managed by a small developer team. So let's say 2 to 3 people for one microservice, and you don't have to have a huge team. It is harder to manage, more, let's say, time consuming, and sometimes also, let's say, from a team building mentality, harder to maintain. So this is referred as a polyglot development. Microservices can be deployed independently and more frequently. Your team can update the microservice without rebuilding or redeploying the entire system. Each microservice is, let's say, representative for a persisting and is responsible for its own data. So whereas a monolithic application only, let's say, has one database and sub-database that is harder to maintain with each, let's say, more, or say, as much as the database gets bigger, it is harder to maintain. So microservices communicate with each other by using well-defined APIs, and this implementation is hidden from each microservices. And the services themselves, they don't need to share the same technology stacks, or libraries or frameworks. So they can be completely independent. And what I want to show you in the next slide is some benefits of this architecture, or modern architecture. So you can update a service without redeploying the entire application, which is very crucial in the modern, let's say, fast-paced business environment. This makes also bug fixes and feature release more manageable and risk-free. A single development team can build, test, and deploy a microservice. This results in a continuous innovation and a faster release cycle. Teams can focus on one microservice. The smaller scope of microservices ensure the code base is easier to understand. Another benefit is when onboarding new team members, they can easily get up to speed, become more productive. And one of the most important parts is if a service goes down, it will not take the entire application with it. So when a service is down, but the rest of the application or the rest of the infrastructure is still functioning. So when change is required in a certain part of the application, the related service has to be modified and redeployed only. And there's no need to modify and redeploy the entire application. Developer can use the latest microservice pattern and firmware as they wish. So technologies such as Docker, containers, Kubernetes get used to host microservices. Teams can pick up the technology as they wish and as the best for what they want to, let's say, to build in that stage. Microservices can be scaled independently. Each microservice can be, let's say, allocated depending on its CPU needs or its memory uses, the memory needs, according to the requirement. But it's not all, let's say, how do I put this? It's not only paradise. Microservices, they bring some problems or let's say challenges with them. And I want to address this also because it's also important to know the challenges to prepare for them. So microservice application have more moving parts than multi-application. So each microservice is simple, but the entire system as a whole become more complex when the number of microservices increases. Data consistency can be a challenge as microservices is responsible for its own data persistency. Microservices architecture can also lead to issue as each microservice can be built with a different technology. So here you see the first one is with Python, the second one with Ruby, the third one with .NET. As a result, maintenance become more difficult. It will be beneficial if you put project-wide standards to follow up when building microservices. In large projects, the number of APIs increased also with the size, and as a result, the communication with APIs increased and they could cause latency issues. You can introduce serialization techniques when designing APIs, as well as asynchronous communication patterns can be applicable. Microservices require also a mature DevOps culture. Update to some microservices might not break other microservices that depend on it. Without a careful design, you may face compatibility issues, and microservices also a distributed system. So to be successful, first evaluate whether the team has the required scope and experience to implement this. We should model each microservice around the business domain. Data storage should be private to each microservices. We should use the best storage for each microservices. Offloading authentication and SSL termination to a gateway. The gateway should handle client requests without any knowledge of the business rules. Otherwise, the gateway becomes a dependency, causing coupling between coupling between microservices. And microservice functionality that are likely to chain together should be packaged and deployed together. Otherwise, those microservices end up being tightly coupled as a change in one microservices require updating the whole microservice. And then we have the same game again that, almost monolithic infrastructure. In this case, I want to show you an example of a microservice architecture. So let's look at this example. This is a fictitious example. You have some time web application that you want to serve, and that is has a backend API that you want to communicate with, or perhaps a public API that your customers can interact with. So we have here a client, your customer maybe, and then they will have to hit some type of endpoint, and this is usually managed by an API gateway. This can be managed within Kubernetes itself. I will talk about Kubernetes in another point. And the microservices themselves are all managed and orchestrated via Kubernetes. So depending on the endpoint that your client hits, it will point to the correct microservices within your Kubernetes cluster. In this example, there is communication between other microservices within the cluster, but it's important to note that each of these microservices are completely independent. The last thing I want to cover before we move on, it's more or less my microservice methodology that I always implement while creating new services. And these are exactly 3 points. So the first would be keep it small. So we don't want to create a new monolithic infrastructure. So keep it small. Keep it decoupled. If, for example, I notice I'm pulling in a class or an object from another package in my repo, then there is something wrong with my structure or my infrastructure, and I will need to look at services communication instead. And lastly, microservices should embrace the Unix philosophy, which states do one thing and do it well. So if you take these 3 points into consideration, and you should understand creating microservices should be focused on doing one thing and doing it very well. This is an example of an e-commerce system that is built on microservices that covers a lot of, let's say, the activities on the website with really, really decoupled technologies, using different backend technologies, and using, let's say, for each business part of the website, a different microservice. All right, but let's say the use of container for building successful microservices architecture is inevitable, and Docker is a technology that we can use for this code. But what is Docker? I mean, everyone is hearing this in the news everywhere in social media, but I'm trying to, this is my attempt to, for a simple explanation. So Docker is a container platform that allows you to separate your application from the underlying infrastructure by building up your code and all of its dependencies into a self-contained entity that will run the same on your supported system. So picture an actual physical shipping container, and you can use shipping containers to transport anything that will fit inside. So since shipping containers come in standard size and they are easier to manage because they're consistent, it really doesn't matter what's inside the container, because the infrastructure used to transport them is the same. The ship are able to transform them, trains are able to move them on and off the ships, trucks are able to transport them, and none of the infrastructure is concerned what is actually in the containers. So when it comes to the software development, it's not the initial development that is actually challenging, it's everything that comes after that. So deploying code is a challenge. Managing dependencies is a challenge. Handling rollbacks is a challenge. All of these things are made more challenging because the development environment are rarely identical to the production environment. And this is where Docker containers can help. So Docker containers are similar to their physical, let's say, pendant. They allow you to take whatever software you need to run, bundle it into a consistent format, and run it in any infrastructure that knows how to handle the container. The end result is kind of like having a single executable for all your code. It's similar to an app on your phone. All the code is bundled into one single unit, and it's going to run on my phone, on your phone. It's similar. It doesn't really matter. So so having your code inside a container means that it's isolated from other processes and other containers. So each container can have its own process space and its own network stack and resource allocation. So Docker containers are often compared to virtual machines because virtual machines are, let's say, familiar for most IT people. However, they are pretty different. When you're running a virtual machine, the OS that you're using in the virtual machine is running on virtualized hardware. That means that you're using software to emulate hardware and then running the full OS on top. Now, virtual machines are great. We've used them for years and years. However, they can be a bit slow to start, and they can consume a lot of resources that you might not need, and they require patching. So also, they take up a lot of space on disk, especially considering they contain thousands of files that your app doesn't really know and need. A small example is like the whole virtual machine can be in the gigabyte area, and in a container is actually in the megabyte area. So with VMs, each OS is running on the hypervisor and consuming a lot of system resources. Comparing to Docker, the host OS and then the Docker engine, they are in the place where in the place of the guest OS. So what Docker is doing is cutting out the guest OS, allowing you to bundle up the system, libraries and binaries to and everything that your app needs, as well as your code, all into one unit that can be executed via the Docker engine. Where VMs run the entire OS, Docker shares the kernel with the host OS. This means that containers can start up about as quickly as any other process, since they really don't contain all the file required to run the entire operation system. And they don't consume all of the resources that a guest OS does. So it allows you to run more of them on the same hardware. Once all your code and dependencies are in the container, they're going to run the same way anywhere, because everything required to have the code running inside the containers will be there. So if your Docker container, if you use Docker container for all your application, then that's going to allow you to standardize on how you deploy whatever you want to deploy, all of your application. So admittedly, this is a very, let's say, oversimplified explanation of Docker. We can talk about this for days, I guess, but I would like to address something other than Docker, which is Kubernetes, because every container has to be orchestrated, which brings us to Kubernetes. So in this case, I would like to give you like a small overview of Kubernetes. It's basically starting with where it's born. Kubernetes was born out of Google's experience running workloads in a production on internal systems. And it is designed to grow from, let's say, tens, thousands, or even millions of containers and manage them. Organizations adopting Kubernetes increase their velocity by having the ability to release faster and recover faster with Kubernetes self-healing mechanism. So Kubernetes is a distributed system, multiple machines and configured to form a cluster. Machines may be a mix of physical or virtual, and they may exist on-prem or in cloud infrastructure. Each with their own unique hardware configuration. So it doesn't really matter what kind of hardware is behind the cluster. Kubernetes places containers on machines using a shuttling algorithm that consider available compute resources, request resources priority, and a variety of other customizable constraints. So you can set up how you want to manage your containers, and Kubernetes will take care of the orchestration. It's, from the name, orchestration software. Kubernetes is also smart enough to move containers to different machines as their machines are added or removed. So Kubernetes is runtime agnostic, which means that you can actually use Kubernetes with different container runtimes. So Kubernetes also provides excellent and user abstraction by using declarative configuration for everything. Your engineer can quickly deploy containers, wire up networking, scale and expose the application to real, let's say, world scenarios. But not only the engineer are well taken care of, the operations staff are not left in the dark either. Kubernetes can automatically move containers from failed machines to running machines. There are also built-in feature for doing maintenance in a particular machine. Multiple clusters can also join up with each other to form a federation. This feature is primarily for redundancy. Such that is one cluster dies, containers will automatically move to another cluster. The following features also contribute to making Kubernetes, let's say, a top choice for orchestrating containers or containerized application. The automation of the deployment, rollout, and rollback, seamless horizontal scaling, secret management, service discovery, and load balancing, support for both Linux and Windows containers, which is a huge bonus. There is no iOS containers. It's just because Apple is not interested in this technology yet, or I don't know why, but support is only for Linux and Windows containers. Simple local action, stateful application support, persistent volume management, CPU and memory, quota batch, job processing, and role-based access control. So again, this is an oversimplified overview for Kubernetes, but modernizing your infrastructure and your application and utilizing the full power of containers and container orchestration will really give you the best chances to ensure your business continuity. So disaster recovery can be made in a simple way, but you can also invest some time to modernize your application and have the best scenario of disaster recovery when your downtime is at 0.
I hope you learned something from here.
One last sentence from my side. Yeah, one last thing from my side. We had really an overview and a very high-level overview of different matters. So each and every point Michael talked about or I talked about can go much deeper. So we would love to invite you to our next webinar. So we go the dive into disaster recovery, Docker, and Kubernetes. And I hope you enjoyed this let's say quick webinar. Thank you.
Yes, we hope you learned something, giving you a rough overview about the topic of disaster recovery. And feel free to contact us for any further question, and hope to see you next time. Thank you very much and have a good time.
Thank you, guys. Take care. Bye.
Bye-bye.